Kinetic molecular theory. This is the simplest model for the behavior of gases, and it works pretty well. And the name is descriptive. Kinetic has to do with movement, molecular, so it's the theory explaining gases by the movement of the molecules. So we model a gas as a collection of particles, which could be atoms or molecules, depending. And these particles are in constant motion. And I talked to you a little bit about this before. We can think of it kind of as the molecules are like the little blip in the Pong game, and it just keeps going until it runs into something. So important things to know: the size of the particles of these gases is so small in relation to the volume of the whole gas that we can just forget about it, basically. It's negligible. We can neglect it and be just fine. We assume that the gas particles occupy no volume, even though they have mass. Now, do they have volume? Sure they do. But it's just so small that we can neglect it. So kinetic molecular theory says the size of a particle is negligibly small. There is a lot of empty space in a gas. As an example, the argon atoms at STP occupy only 0.01% of the gas volume. Well, that doesn't mean very much. But if an argon atom was the size of a golf ball, its nearest neighbor would be 4 feet away. So you can picture that. Golf ball, argon atom, okay, its closest neighbor is going to be 4 feet away. There's a lot of empty space in the gas. Solids and liquids are not like that. Another important thing about kinetic molecular theory: the average kinetic energy of a gas particle is directly proportional to the temperature in kelvins. When you raise the temperature of the gas, the average speed, the average velocity of the particles increases. I have to throw in a physics equation here. Kinetic energy is 1/2 the mass of the object times its velocity squared. When you raise the temperature of a gas, does the mass of the particles change? No. The kinetic energy changes. Something has to change. It's the velocity. So higher temperature, particles moving faster. Important to recognize, though, this is the average kinetic energy. Okay? Not all those gas particles are moving at the same speed. Some are going slow, some are going fast. The average increases as you raise the temperature. The collision of one particle with another is completely elastic. And that's from physics 2. What that means is that when those two particles collide, they can exchange energy, but there's no overall loss of energy. Meaning the energy cannot be lost to something non-useful like heat. So here we have an example. Billiard balls are pretty elastic. And when they bounce off of each other, so here we've got, which direction are the arrows? So we've got this ball coming in this way, this ball coming in this way. They collide and they go off in opposite directions, and they're going pretty much the same speed as when they came in. It's not perfect because they're large objects, but that's an example of a pretty elastic collision. Here's 2 lumps of clay. You roll those at each other and they just go and stick together. They don't even bounce off of each other. They actually make that noise. I'm not going to make it again. But they do that. So what happened to the kinetic energy that those 2 lumps of clay had? Energy can't be created or destroyed. It's dissipated as heat. So in an inelastic collision, the kinetic energy gets dissipated as heat. That is not happening with gases. So because when the gases collide, the particles, they don't lose any energy, they just can keep on moving like that infinitely. They don't need to get more energy. You don't have to give them a push now and then to get them going again. They just keep going. Those particles are constantly moving. And they're going to run into each other. They're also going to run into the surfaces or the sides of the container. When they hit the container, they exert a force. I think we'll come up on this later, but I'll show it to you right now as well. The force is the mass times the acceleration, if you're interested. Oh, didn't mean to do that, but that's fine. So the pressure is force divided by the unit of area. So the force from those particles divided by the area spread out over whatever area it is gives rise to the pressure. So these concepts of the kinetic molecular theory of gases explain the laws that we've talked about. Kinetic molecular theory is a theory. A theory explains why something happens. A law just says what happens. Boyle's law just says the volume of a gas is inversely proportional to the pressure. It doesn't say why. Kinetic molecular theory helps us to understand why. When we decrease the volume, that forces the molecules into a smaller space. So more molecules are going to be colliding with the container at any given instant, and that increases the pressure. Smaller volume, higher pressure. You squeeze those particles together, they're going to be colliding with the walls more frequently, and so the pressure is greater. It explains Charles' law. Volume of a gas is proportional to the absolute temperature. So kinetic molecular theory says that when we increase the temperature of a gas, the average speed and thus the average kinetic energy of the particles increases. If we want the pressure to stay the same, which is what Charles' law says, then we have to have a greater volume to spread the collision out over a greater surface area in order to maintain that pressure. If we don't allow the volume to change, the pressure will increase. But Charles' law was dealing with something at a constant pressure. At a constant pressure, then the gas will expand. It will get larger when you increase the temperature. Some concerned looks about that one. Avogadro's law. Volume of a gas is directly proportional to the number of gas molecules. Well, if we increase the number of gas molecules, then we're going to have more of them hitting the wall. If we want to keep the pressure constant, we're going to have to increase the volume again. Because if we keep the volume constant, the pressure is going to go up. Any questions? My son once sat in his freshman calculus class. His teacher said, "Does anybody have any questions?" And he was sitting there thinking, "I have lots of questions, I just can't put them into words." Right? Anybody there? Like, I don't know what you're talking about, but I can't formulate a question about that. Yeah.
Okay.
Freshman in college, yeah, that would be crazy, wouldn't it? My kids are crazy, but not that crazy.
So when the sun's producing all that energy, the energy's already in the atoms when it's fusing?
The energy from the sun comes in the form of electromagnetic radiation, and when that interacts with matter, then it generates heat energy. Yes?
Are the volumes of the particles always
Negligible?
Yeah.
It's hard to say, isn't it? Are the volumes of the gas particles always negligible? No, under certain conditions they're not, and we're going to talk about that. And Pivner is called the ideal gas law, and it describes an ideal gas. It's like a perfect child. Is there such thing as an ideal gas? Actually, no. But under certain conditions, many gases behave very close to ideal. But I'll tell you more than you want to know about that later. Kinetic molecular theory explains Dalton's law as well. Dalton's law is the total pressure of a gas mixture is the sum of the individual pressures of each gas in the mixture. Well, kinetic molecular theory says the particles have negligible size and they don't interact with each other. So if you have particles of different masses, they're going to have the same average kinetic energy. Kinetic energy is mass times the velocity squared divided by 2, 1/2 mv squared. So the fact that they have different masses doesn't matter. The average kinetic energy is the same, and so the total pressure of the collisions is the same, even though some of the particles are bigger than other particles. It's the kinetic energy that they have, not just their size. It's the relationship of the size and the velocity. So essentially, all gas particles behave the same. Okay, so kinetic molecular theory and the ideal gas law. The kinetic molecular theory is actually a quantitative model that implies PV equals nRT. And I'm going to show you how that works out. So the pressure on a wall of a container that's occupied by gas particles in constant motion is the force due to the collisions divided by the area of the wall. So the pressure exerted here is the force of particles hitting this wall. We're just going to look at one wall here. It's the force of all the particles hitting divided by the area of that wall. Newton's second law tells us that the force of a collision is the mass of the particle times the acceleration due to the change in direction. So that says the force of a collision is equal to the mass of the particle times the acceleration. What happens when something hits the wall? It's going in one direction, it stops and moves in the other direction. That's a change in velocity. A change in velocity is acceleration. So the acceleration is the change in velocity in a given time interval. So acceleration is the change in, the delta means change in velocity divided by the change in time. For a particle hitting a wall, the change in velocity is twice, the change in velocity is twice the velocity. Because it's going plus v into the wall, it bounces off, now it's going minus v. So delta v equals 2 times v, whatever v is. So we can put these ideas together. Now we can say that A is, instead of delta v, it's 2v over the change in temperature. So I'm taking this, plugging it into that equation to get this, and then we're going to plug this into that guy. And
Did you say change in temperature or change in time?
if I said change in temperature, that's not what I meant, but I think I really did say that. Change in velocity and change in time. I probably screwed up the time. It's a change in time. Change in velocity divided by the change in time. So the change in velocity is 2v, still divided by t, and the force of a collision is the mass times the acceleration, which is 2v over delta t. I'm not going to make you derive this. Awesome, yes. I would like you to follow along, though. Try to follow and understand where I'm going with this, because this is the sort of thing that scientists do, and this is how we come up with some of these laws. So there we have the force of one collision. The number of collisions in some time interval delta t is going to be proportional to the number of particles that could reach the wall during that time, which would be all particles within the velocity and times delta t of the wall. Because velocity is distance per unit time, right? And if you multiply that by time, you get a distance, right? So what that is saying is that any particle in here that's traveling at the velocity v within a time delta t would be able to hit the wall. So it's related to, the number of collisions is related to the number of particles within that volume. So we say, let's see, the number of collisions is proportional to, well, actually I don't want to do that just yet. So those particles are occupying a volume of this distance times the area, because the volume of a cube is length times width times height, right? So here's the length, and there's the width and the height. The width times the height is the area of that wall we're interested in. We're taking that area times this distance, and that is the volume that those particles are in. So this equals the volume that those particles in. If we want to find out how many particles are in there, it's going to be the volume times the density. The density is the number of particles, or the moles of particles, divided by the volume. So the number of particles is going to be the volume, which is velocity times delta t times area. So that's the volume, times the density, that guy. That's the number of particles. The number of collisions is proportional to the number of particles. The total force on the wall is the force of each collision times the number of collisions. So total force is equal to the number of collisions, which was proportional to the number of particles, times the force of each collision. So we're going to say the number of collisions was I wrote this backwards. My head hurts already. I don't want to make it hurt anymore. The force of each collision times the number of collisions. I don't know why I did that backwards. The force of each collision was the mass times twice the velocity over the change in time. And the number of collisions from the previous page was the velocity times the change in temperature times time, change in time, good grief, times the area times n over v. So this is one slide before, and this was before that. Two sections there. This is the force of each collision. This is the number of collisions. And I really shouldn't put equals here. This is proportional. Well, we can kind of combine some things here. These delta t's cancel out, and we've got two of these velocities here. We're doing a proportional equation here, and so this 2, we can just make him go away. We're going to bring a proportionality constant in later. The 2 will get rolled up into there. So the total force is proportional to mv squared times a times n over v. That's an A. Doesn't look like it. So that's the total force. The pressure is the force divided by the area. So the pressure is proportional to that force, mv squared, times A times n over V. This whole thing divided by area. Pressure is force divided by area. So this area cancels out. And now we've got, let's just rewrite the whole thing. The pressure on the wall is proportional to mv squared times n over V. The pressure is proportional to 1 over the volume. That was Boyle's law, wasn't it? And the pressure is proportional to the number of moles, Avogadro's number. So both of those laws are hiding in here. You do not need to know all this, no. You're going to have a new understanding for how cool gas laws are. Okay? So, mv squared times n over v. So that's, I just copied that down from previous. So we've got Boyle's law and Avogadro's law that are hiding in this proportionality here. Kinetic molecular theory says that kinetic energy, 1/2 mv squared, is proportional to temperature. Look, there's mv squared. The 1/2 gets rolled into the proportionality. So now we've got pressure being proportional to temperature times n divided by volume. The pressure is proportional to nt over v. So that's starting to look a little bit familiar. If we throw in a proportionality constant, it becomes an equality, and we get P equals nRT over V, or to get rid of the fraction, PV equals nRT. That's the whole point. Yes, yay! So this, well, why am I doing all this? Well, one thing, I think it's kind of cool, but that's not why I'm torturing you with this. The ideas of kinetic molecular theory are where we started this whole derivation with. Okay? Each of these equations and things that we pulled in together was ideas of kinetic molecular theory. We put those together, it gives us the ideal gas law.
And that's technically physics, right?
Yes, you could.
Back to this.
Yeah, there's a lot of physics involved. All of the sciences overlap, and this is a place where chemistry and physics definitely overlaps. Because we're not talking about chemical reactions here. We are talking about the behavior of matter, but we are talking about the behavior of matter in a very physics sort of way, of mass and acceleration and all kinds of things like that. And that's why if you're a chemistry major, they make you take a year of physics, because you have to understand some physics to really get into chemistry. But this ideal gas law, the law that says this is what happens, they discovered that empirically through experiment before they came up with this explanation of how the molecules behave. But this agreement between the theory and the law and how they mesh together so well gives us a lot of confidence that this is correct. So, kinetic molecular theory predicts behavior consistent with observation and measurement. And theories in science are the most powerful kind of scientific knowledge because they explain what's going on. Now, this model is not perfect. It breaks down under certain conditions. but even looking at places where it breaks down helps us to understand it even more. Here your book goes into a bunch of other derivations that I will spare you from. I'm only going to do that one for you. So, kinetic energy is 1/2 mass times the velocity squared. So in kinetic molecular theory, we said the velocity of the particles is related to their temperature, but not all the particles are going at the same speed. Some are going faster and some are going slower. So because the gas particles have different masses, the only way for them to have the same kinetic energy, to be at the same temperature, is if they have different average velocities. Now, they don't actually use average velocity, because I think to do a real average velocity, you'd have to find the velocity of each particle and add them up, and how do you do that? We actually use what's called a root mean square velocity. So that's what URMS means. It's the root mean square. It's a special kind of average. And root mean square, so URMS, root mean square means we take the velocity squared, we average it, and then we take the square root of that. It ends up being really similar to the average, and so you can think of it as an average, but just recognize it's not actually an average, it's a special kind of an average. So then the kinetic energy ends up being 1/2 Avogadro's number times the mass times, this would be the root mean squared, the velocity squared. So what do you need to know about that? Well, you can take all of that and you can derive this. In a gas mixture at a given temperature, the lighter particles travel faster than the heavier ones, and there's a mathematical relationship. So here's the root mean square velocity of gas particles is equal to 3RT over capital M, where here this capital M, notice it's kind of curvy, that's the molar mass, and it's the molar mass in kilograms per mole. And in the example, I'll show you why that is. This is a different value for R. It's equivalent, it just has different units. This has units of joules per mole Kelvin, and so we use it here because the units work out. If you need that guy, I'll give him to you. I won't make you memorize that one. You should memorize the other one, 0.08206 liter atmospheres per mole Kelvin. And if you do enough homework, you'll memorize it without even trying. So this is the relationship. This right here, little deal, okay? So if you're going to just skip over something, this would maybe be a thing to skip over. Calculate the root mean square velocity of water at 150 degrees Celsius. So the root mean square velocity equals, remember that equation? You've got it probably on paper in front of you. 3RT over the molar mass square root, where R is 8.314 joules per mole Kelvin, and the capital M is molar mass in kilograms per mole. So to calculate this velocity for water, we need its molar mass in kilograms per mole. What's the molar mass of water in grams per mole? 18.02 or 0.016 depending. So that's grams per mole. We need to convert that to kilograms. To convert grams to kilograms, we're going to move the decimal point 3 places over here. Or we're dividing by 10 to the third grams times kilograms. We end up with 0.018016 kilograms per mole. (150 degrees Celsius), I have to convert that So that ends up being, what, 323? No, 423. 423 Kelvin. So the average, the root mean square velocity is 3 times 8.314 joules. I'm on a collision course. Joules per mole Kelvin will slant down here. Change course. Times the temperature, 423 Kelvin. And that's going to be divided by 0.018016 kilograms per mole. Boy, this is one of the ugliest slides I've done. That's just crooked, is what that is. So let's cross out the units that we can. Moles are going to cancel out, and kelvins are going to cancel out. And let's not worry about the rest of them for a minute. Let's get the number. So we have 3 times 8.314 times 423 divided by 0.018016 equals, and then I have to take the square root of the whole thing, and I'm going to end up with 765. The units I'm left with are joules per kilogram, but those are still under the square root. Okay, so here's physics again. So 765. A joule is a kilogram meters squared per second squared. And that's divided by kilograms, and we get the square root of that whole thing. The kilograms cancel out. The squares go away when we take the square root, and we end up with 765 meters per second. It's hard to get meters per second out of liter atmospheres. And that's why we use joules. Physicists have a lot of fun with metric units. So, what do you need to know how to do with that? You need to know how to do just a problem like that. I will give you this. I won't make you memorize that. Okay? You have to remember that capital M is kilograms per mole. You know what? I'll actually give you this too.
Do we need to remember the units of joules?
Well, here, I will put an orange box around things I will give you. So I'll give you this. And I'll give you this. You need to know to put temperature in Kelvin, and you need to know that this capital M is moles per liter, kilograms per mole. Yeah, molar mass in kilograms per mole. And then the units will end up being a velocity unit, meters per second. So this is something that, if you want an A on the exam over this material, pay attention to this. Okay? If your goal isn't quite that high, this particular one you could probably safely ignore. But there it is. I'm supposed to teach that to you, so I did. This is a graph of, I can't read that. Relative number of molecules with the indicated velocity versus molecular velocity. So here, the molecular velocity in meters per second going up here. And at a given temperature, pressure, here are these different colored lines correspond to different gases. And so we see that hydrogen, which is the smallest mass particles, is going to have the highest average molecular velocity. So the smaller particles are going to be moving faster, but they also have a much broader distribution than the larger ones. There's oxygen, and it's got a much tighter curve here. If we look at one gas and increase the temperature, we also see that the sharp curve at 273, which would be 0 degrees Celsius, as we go up in temperature, it also broadens out. The velocities increase, but the curve also spreads out. A little bit like if you took cold cookie dough, it just sits there in whatever shape you put it, right? As the cookie dough warms out, though, what happens? It flattens out. So as you warm up this gas, the distribution of velocities spreads out. So it shifts towards higher velocities. But notice, even at this high temperature, you've got some of these molecules that are moving slowly. And you've got some that are moving really fast. And here's where most of them are, right here in the middle. But there's a distribution. And as you heat it up, that distribution gets wider and wider and wider. But the average is related to the temperature. Yes?
Why are they at different temperatures? Like, why does some stay at the lower, different speeds?
Different speeds?
Yeah.
That's a good question.
Like you said, even in like the pure elements, even if it's just O2 gas,
Right.
that's moving slower than the rest.
Right. Any gas, whether it's a pure element or a mixture of gases, the particles are going to have a range of speeds, of velocities. Their average kinetic energy is going to be related to the temperature. You increase the temperature, on average, they're all moving faster. But one of them could slow down. And I think what gives rise to that is those elastic collisions. If you have, well, let's draw a picture. If you have molecule A coming in, maybe with a velocity of 2, and you have molecule B coming in with a velocity of 4, when they collide, there's still going to be that same, assuming these are the same mass, there's still going to be a total of 6, but how it's distributed is not indicated. This one could come in and leave with 5, and the other one could leave with 1. And so then you've got particles. Well, actually, let's do it this way. Let's say they both come in with the same speed. They're both they're same mass, same velocity, and then when they bounce off, this one's leaving with 3, and that one's leaving with 1. One's going faster now, and the other's going slower. I think that's how they end up with varying velocities. Because it's not it depends on how they hit, whether one gains velocity or loses it, or if it's equal. Or any other questions?